Hey guys, this is one video in a series of science videos that I'm preparing to help young adults on standardized exams. And this one is concerned with interpreting data that you would find in a data table. So here's an experiment that somebody has put together, that they have a projectile or a bullet that has been fired towards a block and spring system. And you'll notice they're wanting to measure the distance that the block and spring system compress once the bullet hits it. So in figure 1 to your left, the last image, or the image at the bottom, shows X, the distance the block and spring has compressed after the bullet has hit it. Now, there are many variables that one could measure for this experiment. Let's look at figure 1, the very top of that figure, and notice that you have a bullet or a projectile traveling at some velocity. It's traveling towards a block and a spring system that's tied together. Now, you could change the mass of the bullet by increasing or decreasing it, change the velocity at which it's been fired. You could change the mass of the block by increasing or decreasing it, or you could change the spring stiffness by making it more stiff or less stiff. So just with that in mind, you have a possibility of many different variables in this experiment. Well, in this experiment, if you look at table 1, you will see that the table is divided up into a trial. M sub P, which is mass of the projectile, V, which is the velocity at which the projectile is traveling, and X, the distance which the block and spring compress, and then KE, which is kinetic energy, and PE, potential energy. Notice between tables 1 and 2, we have 12 total trials, or another word you could say is 12 total experiments. Those experiments have been grouped into threes, and they group them into 3 to try to keep the experiment standard across all 12 trials. So trials 1, 2, and 3, they vary the mass of the projectile, or they vary the mass of the bullet by increasing the mass of the bullet. And they keep the bullet's velocity the same. So if we were to increase the mass of the projectile, one would expect that the block and spring system would compress a certain distance as the mass of the projectile increased. Now, notice our variable X in table 1. It, from trial 1 to trial 3, goes to 0.02, 0.04, 0.06. So as we increase the mass of the projectile, the distance in which the block and spring system compress increases, which makes sense. Now notice your kinetic energies. Those kinetic energies have also increased because of the mass of the projectile has increased. Now, when you look at the potential energy category, notice the potential energy is much less than the kinetic energy. Well, it's going to be because the mass of the projectile, as it increases, carries different amounts of energy, and the block and the spring system are not capable of absorbing all the energy that bullet is transferring into the block and spring system. So some of that energy gets lost in the form of heat to the environment. Okay, look at trials 4, 5, and 6. What are we changing now? We're changing velocity. Notice in trial 4, 5, and 6, we start at 10, increase to 15, and then increase to 20. But the mass of the bullet is staying the same. Now, if we increase the velocity, would we expect the distance that the block and spring compresses to increase? Well, at 10 meters per second, you see the distance traveled with a block and spring is 0.041 meters. At 15 meters per second, the compression of the block and spring is 0.061. And then in trial 6, it's 0.081. So as we increase the velocity of the bullet and hold the mass of the projectile the same, then we get the X distance to increase. Table 2. Table 2 now has different variables. Table 1, we had mass of the projectile. Now, in table 2, we have mass of the block, M sub B. And we also, in table 2, have K. K stands for the spring constant. So now they're testing what happens when the mass of the block increases and you have a constant spring tension. As the mass of the block increases, we would expect the distance that the block and spring system compresses to decrease. And look what happens. As the mass of the block increases, the distance that the spring compresses decreases. It starts at 0.086, 0.061, and then in trial 9, it's at 0.050. Look at your kinetic and potential energies. They're still different. Now, look at trial 10, 11, and 12. What are we changing now? We're changing the spring constant. We are making the spring more stiff. In trial 7, 8, 9, it was at 3 newtons per meter. And in trials 10, 11, 12, it's going to be varied from 5 to 7 to 9, making it much more stiff. But we're going to keep the mass of the block the same at 1 kg. Well, if we make the spring more tense, wouldn't it be that the block and spring would decrease less? Well, let's look at the value of X. What does the value of X do as we increase the spring tension? And as we increase the spring tension in trials 10, 11, and 12, the X distance in 10 is 0.067. In trial 11, it's 0.056. In trial 12, it is 0.050. So therefore, you can increase the spring's tension and decrease how the block and the spring compresses in trials 10, 11, and 12. In trials 7, 8, and 9, you can increase the mass of the block and decrease the distance that the spring and block compress. In trials 4, 5, and 6, you can increase the velocity, hold the mass of the projectile the same, and therefore you can cause the block and spring system to compress more. In trials 1, 2, and 3, you can increase the mass of the projectile, hold its velocity the same, and cause the block and spring system to compress more as we increase the mass of the projectile. Now, anytime you see a data table on the ACT or the SAT or any standardized exam, this is how you should read them. Once you give them this type of intentional focus, then any of the questions that they have created for you will be very simple to identify. I hope this helps. And as always, I wish you all the luck, and you can always reach out to us if you need any help.